Imagine trying to build a state-of-the-art skyscraper, but instead of spending billions, your final construction bill is, well, basically pocket change. That is essentially what we are looking at today for you, our listener, on this deep dive. We are exploring a massive stack of technical reports on Kimi K3, which is an open-weight AI dropping on July 27, 2026. And okay, let's unpack this because it is fundamentally breaking the pricing physics of the tech world.
It really is a fascinating disruption. I mean, the benchmarks we are looking at show a system completely matching proprietary closed source models from Western developers. We are talking heavyweights like Claude Fable 5 and GPT-5.6 Sol.
Right, the massive
Yeah, the
ones.
really big ones. But here's the critical shift. Kimi K3 operates at just one-third of their cost. So we are watching top-tier machine intelligence transition from, a luxury good into an everyday accessible
So
commodity.
wait, you can't just slash prices by two-thirds without cutting corners somewhere, right?
Yeah.
Because K3 boasts 2.8 trillion parameters. Running something with that sheer scale should absolutely melt a standard server farm.
You would totally think so, yeah. But they sidestep that with a highly optimized mixture of experts or MOE architecture. Specifically, they use this thing called stable latent Mo.
Okay, stable latent mode. How does that actually work in practice?
Well, out of 896 distinct neural networks, or experts, the model only fires up 16 of them per token during a task. And the key to making this work without the system just, crashing is a technique called quantile balancing.
Wait, break down that quantile balancing part for me. If the system has 896 options, how on earth does it instantly pick just 16 without lagging out while trying to make the choice?
Right, so it basically acts as a ruthless traffic cop. In older systems, certain expert networks would get bottlenecked with all the complex math while others just, well, sat idle.
Oh, so some parts were overworked and others were doing nothing.
Exactly. Quantile balancing mathematically forces the workload to distribute evenly across the experts in real time. So it prevents systemic traffic jams, stabilizing the massive parameter count.
Oh, that makes total sense. It is like walking into a modern mega hospital. You don't consult all 896 specialists in the building, because that would take years.
Right, you'd never leave.
Exactly. The front desk, which is like the quantile balancer here, instantly routes you to the exact 16 doctors you actually need. It makes sure no single doctor's waiting room is overflowing, so you get world-class care without paying the entire hospital staff.
That is a perfect analogy. But, once you are in the room with those 16 specialists, they still need to process your entire medical history.
Which is the context window, right?
Yeah, exactly.
Yeah.
For AI models dealing with huge context windows, recalculating historical data over and over usually balloons the key value cache memory footprint, and that really drags down performance.
Which brings us to their memory architecture, Kimi Delta Attention, or KDA. I was looking at this, and it seems like they're basically cheating the memory constraints.
It is a very clever workaround, I have to say. KDA compresses those massive, long context histories into linear memory. So instead of rereading the entire document for every new word it generates, the system only performs heavy mathematical attention on the incremental new information.
What they call the delta tokens,
Spot on. The past is summarized, and only the present is actively calculated.
which explains how they cut that key value cache footprint by 75% and boost decoding speeds by 6.3 times. It is like binge-watching Game of Thrones.
Oh, how so?
Well, you don't re-watch the first 5 seasons right before starting a new episode. Your brain keeps a compressed, linear summary of all the betrayals and alliances, and you only actively process the new plot twists, the deltas.
Yeah, that cognitive shortcut translates perfectly to computational efficiency, but none of this algorithmic elegance matters if you can't physically move the data across standard hardware without congestion.
Right, and here's where it gets really interesting, and maybe where I am a bit skeptical. Even with compressed memory, pushing data across standard Hopper-class GPUs usually requires ultra-expensive specialized interconnects to avoid bottlenecks.
True, but they bypassed the physical hardware limits using software-level quantization emulation. It dynamically compresses the data into 4-bit formats right on the standard GPUs.
Wow, 4-bit. That's tiny.
It really is. By dropping the precision down to 4-bit just during transmission, the data takes up significantly less physical bandwidth.
So they're essentially flat-packing massive data structures, sort of the way IKEA flat-packs a bulky couch so you can fit twice as much on a standard delivery truck.
That is the exact mechanism, yeah. Once the data reaches the next chip, the emulation unpacks it. This digital flat packing cuts cross-card communication overhead by 50%.
So it completely solves the physical network congestion without needing exotic hardware. That is wild. And when you put all these mechanisms together, the benchmarks are staggering.
They really are. K3 debuted at #1 on the UC Berkeley front-end code arena with 1,679 points. And on artificial analysis, it scored 1,668 for long-horizon agentic workflows.
Meaning it's doing real complex work.
Yeah, I mean, it is autonomously doing multi-step chip design and running complex astrophysics research pipelines. It is incredible.
You take elite-level intelligence, route the workload like a mega hospital, summarize memory like a TV binge watcher, and flat pack the data to run on standard hardware for a fraction of the cost.
It changes everything.
It really does. Which leaves you, our listener, wondering, if open-weight models can autonomously design computer chips with minimal human supervision at a fraction of the cost, what happens to the value of human entry-level intellectual labor in a world where elite intelligence is practically free?